Okay, for this next part of the practice questions, we have a deck of 18 cards. So these are the 18 cards. Each card has a shape, which is square, circle, or triangle. It has a number of shapes, 1, 2, or 3. So these cards have one shape, these have two shapes, these have three shapes. And then it has a color, which is black or white. So the black shapes are these ones, and the white shapes are these ones. We will draw 3 cards in order without replacement. What is the probability of getting 3 cards that are... Okay, and so we have a bunch of different questions here. So for all triangles, I'm just going to multiply the probability of getting a triangle for my first card times the probability of getting a triangle for my second card, given that I've already taken one triangle out. So this will be probability of triangle first times probability of triangle second, given that I already took a triangle first. And then lastly, times the probability of getting a triangle third, given triangle first and second. Okay, that's one way to do this problem. Another way to do it, I'll show you in a second, but all right, so probability of getting a triangle first is there are 6 triangle cards out of 18 cards. So this is 6 out of 18. And then the probability of getting another triangle once I have already taken a triangle out, because I'm drawing without replacement, how many triangles will be left? There'll be 5 triangles left. And how many total cards will be left? There will be 17 cards left. And then for my third number here, probability of getting another triangle, given that I've already taken 2 out, there'll be 4 triangles left out of 16 cards left total. So this is one way of doing it. Another way you could do this that would be equally good is on top put the number of ways to get 3 triangles, and on the bottom, number of ways to get any 3 cards. Okay, so if you want to do it like this, then you would look at the number of options for the first card, the second card, and the third card. So there's 6 triangle cards, so 6 ways you could get the first triangle. Then after you take one, there'll be 5 triangles left, and then 4 triangles left. So you see here that you end up getting the same numbers, so it doesn't really matter which approach you take. On the bottom, the number of ways to get any 3 cards, there's 18, and then after you take one, there's 17, and then after that, there's 16. So you get the same number either way, it's just a different approach to it, and either way is fine. Okay, number 19, all black. So we're still doing 3 cards in order without replacement. What is the probability of getting 3 cards that are all black? So whichever way you want to do it, there are 9 black cards. Maybe I'll do it the second way because I think we practiced that a little bit more in class. So the number of ways to get 3 black cards is, there's 9 ways to get your first black card, and then there will be 8 ways to get your second black card, and then there will be 7 options for your third black card. And then the denominator here is going to be the same as the last problem, any 3 cards. Okay, for number 20, all triangles and all black. So we're looking at only this group of 3 cards here, the black triangle cards, because we're still just drawing 3 cards. So if they're going to be all triangles and all black in the same 3 cards, then it must be those actually 3 cards. So you might think it's only one way, but we're doing this in order, so we still have 3 options for the first card and 2 options for the second card, and then 1 option for the third card. So this will be 3, 2, 1. And then on the bottom, the same as the last questions. Okay, so now for an interesting one, all triangles or all black. So we're doing probability or formula. So the probability of all triangles or all black is going to be probability of the first event, all triangles, plus probability of the second event, all black, minus probability that both events happen at the same time, which is the number 20 question that we just did. So basically we're adding the answer to number 18 plus the answer to number 19 minus the answer to number 20. Okay. All right, so this is going to be, I'm just going to paste these answers into here. And for my purposes, you don't need to simplify this Some other professors might ask you to simplify it or put it in a calculator, but this is fine for me if you just leave the answer like that. Okay, next question, all the same shape. So now I haven't told you what shape, just what's the probability that the 3 cards you pick are all the same shape. So we're going to do this the same way as we did all triangles. On the top, we'll do number of ways to get 3 of the same shape. And on the bottom, number of ways to get any 3 cards. So on the top, I guess I could do any of those 18 cards for my first card. So 18 options. But then when it comes to my second card, I need to match the same shape, right? So once I've picked one card, I know what shape I need to match after that. Let's say I pick a square first. Then after that, there will be 5 squares left. So the second number here will be 5. And then after that, it will be 4. Denominator is still going to be the same for all of these. It's just the number of ways to get any 3 cards. Number 23, not all the same shape. So I've just taken 22 and I've put the word not in front of it. So I'm going to use the probability formula for not. So not all the same shape is 1 minus the probability that they are all the same shape. So this is going to be 1 minus my last answer. By the way, you can cancel the 18s from the top and bottom here if you want to. Number 24, all the same color, is very similar to 22. So on the top, boop, boop, boop. Bottom, oops, sorry, that was the wrong thing on the clipboard there. So all the same color. So for my first card, it can be any color, so 18 options. But then for my second card, it needs to match whatever color I picked first. So then there will be 8 left of that color. So 18, and then 8, and then 7. Okay, not all the same color is going to be just like number 23. In fact, it's so similar, maybe I'll just copy paste. So not all the same color. It's going to be 1 minus probability that they are all the same color. So this is going to be 8 and 7. Okay, I hope it makes sense. Moving along to the next section, continuing with this deck of cards, we are going to draw 2 cards in order and without replacement. And now we're going to do some given probabilities. So what is the probability of getting a black card second, given that you got a black card first? Okay, so probability of getting a black card second, given that you got a black card first. So we're just going to use our regular probability formula, which is number of ways the event can happen, so number of ways to get a black card second, but with the given information, given we got black first. And then on the bottom, same way, it's going to be number of ways to get any card, but given that we got black first. Hold on, I want to think about this for a second. Is this the right way to explain this? I think maybe this is not exactly the way I want to explain this, because the experiment is supposed to be drawing 2 cards, right? But the way I've set this up, it looks like I'm really only drawing 1 card. So maybe let me put a pin in this and try another explanation, and then I'll come back to what I was doing here. So if we do this more kind of formulaically, using the techniques we've been learning in class, what I should put on the top here is number of ways to get, I should put the number of ways to get the out, I've written this question, I've written myself into a corner here with this question. I'm sort of internally debating, like, how do I explain this? Should we do 2 cards on the top and 2 cards on the bottom, or should we do 1 card on the top and 1 card on the bottom? So we could put the number of outcomes that have a black card second, given that you have a black card first. The issue I'm running into is, like, if you do two cards on the top, you've got to do 2 cards on the bottom. If you do 1 card on the bottom, you got to do 1 card on the top. So another way to approach this would be number of, I guess, outcomes that have a black card second. given a black card first. And then on the bottom would be the number of ways, or number of outcomes rather, given a black card first. The point is that you have to make both pools conform to the given condition. Like both the numerator and the denominator need to only include outcomes that are according to this given condition. So only black cards can be considered for these outcomes on the top and the bottom. They both have to be only outcomes that have the black card first. Okay, I think I'm not doing a terribly great explanation of this, but let's see if we can calculate it both ways, and then I'll just point out that these are going to give us the same number anyway. Okay, so the number of outcomes that would have a black card second, given that they had a black card first, so basically the number of ways to deal 2 black cards from this deck is, so if you do a black card first, you have 9 ways to do that. Black card second is going to be 8 ways to do that. And now the number of total outcomes, but only the ones that have a black card first. Well, okay, there's 9 ways to do a black card for the first one. And then after that, we're doing just any outcomes on the bottom. It doesn't have to have a black card second. So at that point, you would have 17 cards left to pick from for your second card. So this does cancel down to 8 over 17. Now, if you look back at the way I was trying to do this first, I was looking at the number of ways to get a black card second, given that you got black first, and that would be 7. So if you'd already taken 1 black card out of the deck, oh, sorry, it would be 8. If you'd already taken 1 black card out of the deck, there will be 8 black cards left. And then on the bottom here, the number of ways to get any card, given that you got black first, there would be 17 cards left in the deck. So you do get the same number regardless of which way you do this. I think maybe I didn't write a terribly great question here, since I made up an event that sounded like you're only going to draw 1 card, even though the experiment is drawing 2 cards. Okay, let's not dwell on that. Let's move on to number 27. Getting a black card first and a black card second. What is the probability of that? Okay, this is easy. Probability of getting a black card first and black card second, you're going to do this. Probability of getting black first, and then you're going to multiply it by probability of getting black second, given that you got black first, which is actually what we just calculated in the last part, even though I belabored it way too much. Okay, so probability of getting a black card first is 9 out of 18, right, or 1/2. So that's our first number. And then we're going to multiply that by the probability of getting a black card first, or sorry, getting a black card second, given that you've already taken out 1 black card, and that's going to be 8 out of 17. Oop. Okay, I'm really all over the place in this video. All right, 28, getting a black card second, given that you got a white card first. So if you've already taken a white card out of the deck, what's the probability that you now get a black card on your second draw? I'm going to not belabor this one. So if you've taken 1 white card out of the deck, you have 9 black cards left to pick from. And how many total cards do you have left to pick from? You would have 17 left if you've taken 1 white card. So this will be 9 out of 17. Now, probability of getting a white card first and a black card second is going to be probability of getting white first times probability of getting black second given white first. So probability of getting white first is 9 out of 18, or 1/2. Probability of getting black second, given that you got white first, is 9 out of 17. Okay, now for number 30, the overall probability of getting a black card second. And the hint here is that getting a black card second can be done in 2 different ways, which are mutually exclusive. You can do it by getting a black card first and a black card second, or by getting a white card first and a black card second. So all we really need to do here is use the probability formula for OR. So probability of black first and black second plus probability of white first and black second. So we're just going to add together these 2 answers from number 27 and number 29. Okay, and I'm going to actually simplify this because this is one situation in which it's kind of interesting. what it simplifies to. So if I was to actually um, multiply these together and like add this all up, you can see that they both have a factor of 9/18. So there's 9/18 here and 9/18 here. So I can actually factor out that 9/18. And then the other part is going to be 8/17 from the first one, and then plus 9/17. Okay, and what is 8/17 plus 9/17? That is a 17/17. So this actually simplifies to 9/18 times 17/17. 17/17 is just 1. So this is really just 9/18, which is 1/2. So actually, the overall probability of getting a black card second is 1/2. So if you have no knowledge of what you got for your first card, the probability for your second card, even though you know you already dealt some card, it's still just 1/2, as if you had never taken anything out of the deck. Kind of interesting. Okay, moving along to number 31. A certain company requires job applicants to take 3 tests, A, B, and C. Associated probabilities are below. So we have these different events. Passing test A, probability is 60%, passing B, 70%, passing C, 50%. Pretty hard tests. Passing B, given that you passed A, that actually raises your probability of passing B higher if you know that you passed A. Goes up to 80%. Passing C, given that you passed B, is much higher probability than passing C alone. Passing A and C, that is a lower probability than either A or C by itself. So passing both of those is kind of a low probability. Okay, and then we have some related questions. What is the probability of passing A and B? So I'm going to use these probability formulas for a series of events from back here. I want to use the ones, I don't want to assume that these events are independent because I've not been given the information that they are, and I think they're probably not independent. I already noted that it looked like some probabilities of passing went up when you had passed other ones. So I cannot assume those events are independent. Then I'm going to use these AND formulas here. So the probability of 2 events happening is the probability of one of them times the probability of the other one given the first one. All right, so this is going to be probability of passing A times probability of passing B given that you passed A. Okay, so that's the formula for, right, let me write out what I'm actually calculating here. Pass A and pass B. Okay, so I'm going to do probability of passing A times probability of passing B given that you've passed A. So the first one is 60%. It's the first row in the table. And then the next one, I'm going to use this row in the table, passing B given that A was passed. So basically 60% of these applicants passed the first test, test A, and then of that 60% that passed A, 80% of those people then go ahead and pass B. And if you were really going to multiply these out, you would need to do it in decimal form like this. And on a test, I would probably not require you to simplify this. But if you wanted to do it, it comes out to 0.48 or 48%. Okay. What is the probability of passing A or B? So now I'm using the OR formula for probability. So probability of pass A or pass B is probability of passing A plus probability of passing B minus probability of doing both, pass A and pass B. So we have to subtract the overlap so that we don't count it twice as part of both of these groups that we're adding together. So we're doing these 2 rows in the table added together, and we're not subtracting a row from the table. What we're subtracting is actually the answer to number 31. That's what we're going to subtract. So this is going to be 60% plus 70% minus the answer to number 31, which is 48%. Or if you didn't want to actually multiply it out, you could just put it in here just like this, like leave it as that product right there. That would be fine. But if you did want to add it together, let's see, 60 plus 70 minus 48, 82%. So 82% probability of passing A or B. Okay, are the events passing A and passing B independent? I'm absolutely sure these are not independent, and the reason I know is I already noted it just when I was glancing through the table. The probability of passing B changes if you know that you've passed A. If you know that you passed A, your probability of passing B goes up by 10%. Look at that. So those two numbers are different, and they're not independent. So this is definitely no. Probability of passing B is, can't type, 70%, but probability of passing B given that you passed A is 80%, which are not equal. Okay, what is the probability of passing A or C? This one I think we can do it from the table. So probability of pass A or pass C is probability of passing A plus probability of passing C minus probability of passing both. And that was actually given in the table, or yeah, that one. So we're going to do this row plus this row minus this row. Okay, so this is 60% plus 50% minus percent, which I think is 6 plus 5 is 11, minus 3 is 8, 80%. All right, and then lastly, are the events passing A and passing C independent? Oh, I don't know. Let's check. So yeah, I don't have any givens that relate A and C to each other, so I think my only choice is to check the third version of the equation. These are the three equations you can check for independence, except I'm going to use A and C instead of A and B. I think I need to use this third one to check because I don't have the givens probabilities involving A and C. Okay, so I'm going to compare probability of passing A times probability of passing C with the probability of passing A and C. So I'm going to check this equation. It's A and pass C. I'm going to check if that's the same as passing A times passing C. Okay, so let me calculate each side one by one. So probability of pass A and pass C, that's given in the table. That's 30%. This row right here. And then if I multiply together probability of passing A times probability of passing C, just overall, these two rows. You know what? I think that is 30% because half of 60% is 30%. So I think they actually are. So this is going to come out to the same number. Okay, these are equal, so they are independent. Interesting. So topics on those two tests must be completely different if the probability of passing them, or if the events are considered independent. Interesting. Okay. Right. Well, that was all the review questions. So send me an email if you have any questions.